In this video, we are going to go over the Kw and the autoionization of water. So water is amphoteric. It can act as an acid or a base. The autoionization of water occurs when a small concentration of water molecules react with other water molecules to produce hydronium ions and hydroxide ions. So we have a base here, one water molecule acting as an acid, another water molecule acting as a base. The acid is going to donate a proton, so this base is going to take a proton, and then you're going to be left with a hydroxide ion and an hydronium ion. In pure water at 25 degrees Celsius, the concentration of hydronium ions and the concentration of hydroxide ions are equal, and they both equal 1 × 10⁻⁷ molarity, or moles per liter. The ion product constant for water, also known as Kw, is the equilibrium constant for the autoionization of water. So this is equal to the product of the hydronium ion and hydroxide ion concentrations. So Kw equals the 1 × 10⁻⁷ times 1 × 10⁻⁷, because both of them are equal to each other. And so Kw is equal to 1 × 10⁻⁴. That's the value of Kw. So knowing that, we can calculate the concentration of hydroxide ions and hydronium ions in a solution, knowing one or the other. So when acid or base is added to water, ionization of water shifts, but the Kw is always constant. So in accordance with Le Chatelier's principle, when the hydronium ion concentration increases, the hydroxide ion concentration decreases proportionally, and when the hydronium ion concentration decreases, the hydroxide ion increases proportionately as well. So as hydronium ion decreases, hydroxide ions increase, and vice versa. So if the hydronium ion concentration increases from 1 × 10⁻⁷ molarity to 1 × -10⁻⁶ molarity, which is a 10-fold increase, then the hydroxide concentration has to decrease by the same amount, and it'd be a 10-fold decrease from 1 × 10⁻⁷ molarity to 1 × 10⁸ molarity. So we know that the concentration of the hydronium ions and the hydroxide ions are equal to 1 × 10⁻⁴. To find the concentration of the hydroxide ions, we can manipulate this equation so that we have the Kw on top, and if we know the hydronium ion concentration, we put it on the bottom. We plug in the numbers, so this would be 1 × 10⁻⁴ over, this would be our new concentration we're looking at. So 1 × 10⁻⁶. Doing this calculation would equal 1 × 10⁸ would be the hydroxide concentration. We have our new hydronium ion concentration, 1 × 10⁻⁶, times 1 × 10⁸. This is our new hydronium concentration, and it still equals that constant 1 × 10⁻⁴. So we have our Kw equation right here, and we can manipulate it 2 different ways in order to determine. We can figure out the hydronium ion concentration if we're given the hydroxide ion concentration, or we can determine the hydroxide ion concentration given the hydronium ion concentration. So to practice, we're going to calculate the hydronium concentration if the hydroxide ion concentration of an aqueous solution is 1 × 10⁻⁻12 molar. So go ahead and pause the video, and when you're ready, we'll come back together and work on it. Okay, so we know that the concentration of hydronium ions and hydroxide ions is equal to 1 × 10⁻⁴. And we know the hydroxide ion concentration is 1 × 10⁻⁻12. So we can rearrange this equation so that to dissolve for the hydronium concentration and have OH minus on the bottom because we divide both sides by OH minus. So plugging in our numbers now, 1 times 10 to the negative 14th over 1 times 10 to the negative 12th. This is equal to 1 times 10 to negative second molar. So this is the hydroxide concentration of this solution. So the relationship between pH and concentration of H3O and OH minus, we see that we have pH of 0 is 1 times 10 to the 0 of hydronium ion concentration and 1 times 10 to the negative 14th of the hydroxide concentration. A lower pH is more acidic, and you're going to have a higher concentration of hydronium ions and a lower concentration of hydroxide ions. And it goes on from 0 to 14. So in summary, in pure water, the concentration of hydroxide and hydronium ions is 1 times 10 to the negative 7th molar. The product of these two concentrations is equal to the ion product constant Kw. At room temperature, Kw is 1 times 10 to the negative 14th. The ion product constant is hydronium ion concentration times the hydroxide concentration, which is 1 times 10 to the negative 14th at 25 degrees Celsius. Using this equation, the hydronium ion concentration can be calculated from the hydroxide concentration and vice versa.